Hey everybody, Mr. Piercy here, and what we're going to be looking at today is something known as the triangle inequality theorem in geometry. The reason why I really want to show you why this is the way it is, or I want to show you where the theorem came from, is because this is something that, while in geometry it's a relatively small thing, it's not going to really be used outside of a triangles unit. But it does seem to be a type of problem that is regularly asked to students on college entrance exams. Why they include so many kind of obscure geometry concepts on college entrance exams, I have no idea. But this is something that does seem to be asked quite a bit. And so I wanted to show you why it exists in the first place and how we're going to be using it as part of our lessons. So the triangle inequality theorem, there's actually going to be two things that we're going to talk about, and I'll get to those towards the end. But this is the first kind of way that we're going to approach it. So we have a triangle that we're trying to form called triangle ABC. Side AB has a length of 8 centimeters and side BC has a length of 5 centimeters. So this is a very common question that I've seen on college entrance exams, particularly I'm thinking about the SAT, is what is the length or what is the range of lengths that the third side, AC, what could it be? So what I've done is I've constructed a segment that is 8 centimeters long. I just measured it with my ruler. And I same thing here for CB. I've constructed it to be 5 units long, or 5 centimeters long. Now, what we're trying to do is determine what are the lengths of the sides that the third side could be. So what I'm going to do is I'm going to copy segment BC with my protractor. And what I'm going to do is I'm going to put an arc from point B. So what this arc represents essentially, if we kept going around, obviously we would see a complete circle that has a radius of 5 centimeters. So what that allows me to conclude is that C can be anywhere on this circumference, and where this is how we're going to demonstrate what the lengths of the third sides could be. So let's just say we have a point right here. Let's just suppose that C is right there. We could have a triangle that we would form here, like this. Well, let's suppose that point C was right here. If point C is right there, we don't get a triangle at all. So we have to have something that's going to be somewhere else along this arc, but not on segment AB itself, because, well, that doesn't give us a triangle. It just gives us a line. So let's see what else we could do. Well, let's go here. Let's say that point C is right here. Well, looking at my construction, we would be able to complete the triangle here. And so now we have here what we have in red, ABC. Okay, and so let me pick, hopefully this one color will show up okay. What about right here? Here's point C. Ooh, didn't write that very well. Here's point C. So now as it connects to point B, I think you get the picture of what's happening here. Segment, as we rotate around the arc, what's happening to segment AC? Well, it starts from being no triangle at all, just a straight line. And so now we're pulling point C up here, and we're stretching it out here, and we're stretching it out here. And ultimately, if we go a full 180 degrees, we wind up back at a straight line, which kind of makes sense. If 180 degrees is a straight line and 180 degrees is a triangle, well, we can't have a triangle that has points A, B, and C on it if they're also collinear because they're creating a line. So what we're able to conclude here is that in this case, AC, first of all, it had to be greater than whatever AB minus BC gave me. Because if all of these radii from B to C, if they're all 5 centimeters, well, 5 centimeters minus 3 centimeters just gives me my straight line right here. We don't have a line. But the third side, the other way, going to an extreme, is that it would have to be less than whatever AB plus BC worked out to be. Because when I added the two together, we wound up with a straight line again. And we can't have a triangle in a straight line existing with the same 3 points if the same 3 points are collinear. So this is essentially what we look at here. We say that the range of the numbers that the third side could be has to be whatever the difference of the two known sides are, and less than whatever the sum of the two known sides are. So that's one of the first things we look at when we're talking about the triangle inequality theorem. The next thing that we really kind of look at in the triangle inequality theorem is, well, now that we know that there's a range of numbers that the third side could be, how do we determine whether 3 numbers themselves can create a triangle? So here's a common thing. This is going to be a less commonly asked question that I've seen on from the College Board. It's really going to be something that is kind of isolated to a geometry curriculum, but it is part of the triangle inequality theorem, so we're going to go ahead and talk about it. We have these 3 segments, AB, BC, and AC, at 8, 3, and 4 centimeters respectively. And what we want to know is, will they form a triangle? Well, let's take a look. I've already constructed again. I've measured these segments to be their appropriate lengths according to the problem. So what I'm going to do is let's copy segment BC. So just like what we saw in the last construction, what I'm going to do is I'm going to create an arc. And anywhere along that arc will be point C from point B. Well, now we're going to copy segment AC. So from point A, I'm going to basically do the same thing. I'm going to make an arc. So that means anywhere along that arc, point is where point C should be from point A. Well, you can kind of see the problem. If anywhere along here is where point C could be, and anywhere along here is where point C could be, well, the 2 segments AC and BC, they don't actually come in contact with each other, so they don't create a triangle. So what that means is that in this case, because AC plus BC is less than AB, then there's no triangle. Now, what about if we look at it like this? So here I'm still using the segment AB to be 8 centimeters, but now I've changed segment BC to be 5 and segment AC to be 6. So again, I've already set these up, so I've constructed these using, all I did was measure it with my ruler. So now we're going to repeat the process. So copying segment BC, I will place the point of my compass at point B, and again, recognize that anywhere along this arc, is where point C should be located. And now I'll do the same thing with segment AC. So from point A, I will make an arc, and again recognize that anywhere along that second arc I just drew must be point C also. So what we're looking for is the point where both arcs that have to contain point C, we're looking to see where do those arcs meet. And that tells me, just like with a lot of things that we see where they intersect, that's where point C for triangle ABC would have to be located if the triangle had these particular dimensions. So the difference between what we were seeing in this example and the last one is that in this case, AC plus BC is greater than the third side, AB. And that means in this case, we are able to make a triangle. And that's essentially what the rest of the triangle inequality theorem is allowing us to conclude. So here is kind of our final, just kind of wrapping things up here. The triangle inequality theorem simply says that the way I can find the range of numbers that the third side of a triangle could be is by taking the sum and the differences of the given sides, and that's how we find the range of numbers of the third side. The second thing that we're able to say is that for a triangle to be formed, the sum of the two smaller sides have to be greater than the third side. Now, the way I'm phrasing it and the way a geometry textbook typically phrase it are slightly different. The way the geometry textbook would probably say it is they would say the sum of any two sides must be greater than the third side. Personally, I think that's fine, but the only ones that really matter is if the two smaller sides are bigger than the third side. So that's the ones I look at. I want to know, are the two smallest values bigger than the third one when we add them? So that's how we look at the triangles to determine what the length of the third side could be, the range of values it could be, and whether certain values of triangles actually produce triangles or not. So that's it for now, guys. Thanks for watching, and if you have any